Right, so hi guys. So today we're going to be looking at logs and all your rules of logs. So let's get going. There we go. Right, so what's a log? Let's look at indices. So as long as you know your indice rules, logs becomes really easy. So essentially, we know, let's take an indice we know, so 3 squared equals 9, okay? And I'm going to write that all in different colors, which will make sense in a second. So 3 squared equals 9. Now this 3 that's over here, that's called your base. So 3 is your base, and this becomes important. So if you look at your calculator, you'll have a button that looks like this. It's log, and we can convert that 3 is our base, which goes into that slot there. So essentially, this is the same as, and we can convert something into logs. So this is going to be the same as log, and it's to the base 3, 9 equals, don't need to get rid of it. So we've got the base 3, 9, which equals, there we go, equals 2. So essentially what you have here is 3 squared equals 9. So that's what you need to remember. If you remember it for 1, you should be able to remember it for everything. So you've got a to the power of x equals n, and that is the equivalent of saying log to the base a. So you'd say a to the power of x equals n. Right? So we can find things out if we don't know the powers. So it doesn't matter how you think about it. There's different methods to thinking about it, but that's, so for example, if you're missing a power, so if you know you've got log 2 to the something equals 3, that's 2 to the power of 3, which you know equals 8. So you can imagine putting it in there. So in your calculator, if you use this button and you put log 28 in, you're going to get 3. So you need to become quite good at shuffling between these. So we'll just do a few just to get you going. So if we've got log 525, I know you've got a calculator, but you're just going to try and think about it. So you're saying 5 to the power of something equals 25. So you're saying, what is that? That would be 2. If we had log 232, what's going through your head is 2 to the power of something is 32, which would be 5. Now, what you have to remember with logs, if you think about it, actually, let's think about log 4, 1. So 4 to the power of something gives you 1, which is going to be 0, because 4 to the 0 equals 1. I could make that base anything. I could make that base 50. Okay, log 51 would always be 0, because anything to the power of 0 gives you 1. What if I had log a to the a cubed? So I'm saying a to the power of something equals a cubed, and that would be 3. Where this kind of doesn't work is if you say log, say 4 to the minus 1. Well, 4, there's nothing that I can do 4 to the power of, which is going to give me minus 1. So that's just not valid. It's not possible. So you can't log negative numbers. So that's what you have to remember. That strictly, you need to remember that really, really clearly. You can't log negative numbers. You end up with a negative number and it's in a question, you've probably done something wrong. Okay, so on your calculator, you will find 3 buttons. You'll have the log button that looks like this. You'll have a button that says ln, and you'll have one probably that just says log. So on the class with calculator, the just log button is above the brackets and the minus sign, and the ln button is next, these two buttons are next to each other. Now, all this is, it's log to the base e, and e is just this very, very special number. So it's like a pi, it's called a natural log. So this just means log to the base e. So if you did ln to the e, they would cancel each other out and give you 1. This is just log to the base 10. So this, for example, if you put in log without any base of 100, you'd be saying 10 to the power of what is 100, you'll come up with a 2. And obviously this one you can use with any base at all. Okay, so now we're going to look at some rules. And once you have these rules, it's exactly like indice rules where you've got powers and you add them. You've got different types of rules, you learn the rules, and it makes it super easy. So if we take indice rules, we know when we do, like, for example, 2 squared times 2 cubed, you do 2 plus 3 and you get 2 to the 5. Right, so the thing here is the 2 has to be the same. In the same way with your log rules, the base has to be the same, otherwise you can't combine them. So there's 3 main rules. You've got log a to the x plus log a to the y equals log a xy. So if I had log base 2, 3 plus log, now notice the bases are the same here, they have to be the same, 4, that would be the same as saying log to the base 2, 3 times 4, so 12. Okay, so it's kind of the opposite way round to what you do with indices. So that's rule number 1. Rule number 2 is if you take them away. So taking them away is the same as dividing this bit here. And the last rule, if you've got log a to the power something to k, so like 2 cubed, for example, the k can come in front. So you get k log a x. And we'll do some examples to that. So those are your 3 rules, and that is it. Those are your 3 main rules. There are a couple of special cases. So there's a couple of things to think about. So if I gave you log AA, so we're saying something to the power of something is itself, that has to be 1. So a to the power of 1 is a. So log 2, 2 is 1. Log 5, 5 is 1. Okay. We already did this one. Log a to a 1 is always 0. And it's not really a special case, it's a case of this, but if I had log of 1 over x, now I know from my indice rules, this is the same as saying x to the power of minus 1, so I can bring that minus in front and I'd get minus log x. Okay, so those are your 3 rules and a couple of special cases. Now, where this will be tested is using these rules to open logs out or to combine them together. So you have to remember adding, that means times, minus is divide, and if you've got something as a power, you can bring it down. So when you add something, the base has to be the same, and that goes all the way for those 2 rules. When you minus or you add, the base needs to be the same. So if we think about that, let's take some examples. So we've got log 3, 6 plus log 3, 7. Log 2, 15 minus log 2, 3. I'll write these up, and maybe what you can do is, as I'm writing them, attempt them, or pause this and, you know, come back and attempt it. So you've got log 10, 3 minus 4 log 10 a half. So let's try combine those. So here our check, our base is the same. We've got an add there, so add means times. 6 times 7 is 42. So if we were to combine this, we'd get log 3, 42. Here we've got a minus, the base is 2 in both cases, means we can divide. 15 divided by 3 gives us 5. Right, here we got to do it in steps. So do you remember when we had something as a power, it could come in front? In the same way, if it's in front, it can come up as a power. So we can't combine these yet because we've got these numbers in front. So what we can do is we can bring this 2 up as a power and we can bring this 3 up as a power. So we'll get log 5, 3 squared, which is 9, plus log 5, 2 cubed, which is 8. And then we've got 9 times 8, which is 72. So we've got log 5, 72. Right, let's have a look here. Now here again, we've got the same thing. We've got a number in front, so we can bring that up as a power. So we get log 10, 3 minus log 10, a half to the power of 4. So that's 1 to the power of 4, which is just 1, 2 to the power of 4, which is 16. And then we're going to have log 10, and we're going to have 3 divided by 1 over 16, which is the same as 3 times 16. So we'll get log 10, 48. So that's the first type of question you may get, which will only be a few marks, but will lead on to something else. The other thing that you can get is when you have logs and you've got to open them out, and they tend to be in terms of x and y. So let's say we had log a x squared y z cubed all over a to the 4. Okay, so we want to separate that out. So we think everything on top is multiplied by each other. And then we've got something divided by in the last bit. So what we're going to do is we're going to say that's the same as log a x cubed plus log a y, because these are the bits that are multiplied, plus log a z cubed minus log a to the 4. Right, so now we've opened it all out. Now we can put the powers in the front. So we'll get 2 log ax, log ay just stays the same, 3 log az minus 4 log aa. But what is log aa the same as? And we know that log aa must be the same as what? So a to the power of something gives you itself. So that has to be, so all of this has to equal 1, because a to the power of 1 is a. So then our final answer would be 2 log ax plus log ay plus 3 log az minus 4. So we can take something that looks horrible to open out, but actually is okay. Right. I'm always worried about doing the next bit because I'm worried by telling you what not to do is you might do, but this is you cannot do this, okay? Do not make this mistake. So I don't know how you, so you would fail if, so bear in mind, log a b plus c is not under any circumstances the same as log ab plus log ac. So you can't open out the bracket like that, because remember this, the correct thing for this is the base is the same, which means you can multiply it together. So it's log abc, which is not b plus c. Okay, so that's first thing, don't ever do. The other thing that students like to do is if I have log a x all squared, let's say all cubed, so the whole thing cubed, this is not the same as 3 log ax. Okay, so that's not the same, because this would be the same as saying log a x cubed, not the whole thing cubed. Okay, so that's really important. It's just that x cubed or just that number cubed. So this is just what not to do. And it's just really super common mistakes, which lots of students do, kind of like cancelling things out in fractions when you can't. Right, so that's your basic laws. Now, once you know these laws, you can actually combine logs to solve equations. So let's take a past exam question, and we'll show you how that works. So this was from an EdXL paper a few years ago. So you've got 2 log 2 x plus 15, you can see that, minus log 2x equals 6. So we can see that on the left-hand side, the base is the same. So we're going to go through those steps to combine things. So step 1, we'll be bringing that 2 up as a power. So we're going to get log 2 x plus 15 squared. Now we've got a minus, which means we can divide because the base is the same. So you've got x plus 15 squared over x, and that equals 6. And now what does this mean? So this means 2 to the power of 6 equals all of this. So essentially we've got 2 to the power of 6 equals everything that's in that bracket. And we can go ahead, open that all out. 2 to the 6 is 64, so you'd get 64x plus 15 squared. You'd open it all out, you'd get a quadratic. We're not going to go into that right now. And then you could go ahead and solve that. So if you were to solve that quadratic, x, you have a calculator, you could put it in, otherwise 25 and 9. So x equals 25 or x equals 9. Now, whenever you have a question like this, double check, because remember, you can never have a negative x. In this case, it works, but if by putting the x into this bit here, you ended up with a minus log, you know that solution is invalid. But in this case, both of these are valid, so you've got 2 solutions to the equation. Okay, so that's the first type of log equation you might get to solve. The second type is if you have something that looks like this. You've got 3 to the power of something equals 20. Now remember, that 3 is your base. So you're going to convert that into log form. So we've got log to the base 3. So 3 to the power of x equals 20. So remember, that's the way it goes. It's to the power equals. So now in your calculator, you literally type using that button, which is log square square, 3 and 20, and you'd get an answer. So say this was, it gives you 2.727 and to 3, I guess, let's just leave it to 3 significant value figures, whatever it asks you to do. Okay, so in the same way, if now it's a bit more complicated and you have 5 to the 4x minus 1 equals 61, my base is 5. So I've got 5 to the power of something, and the power in this case is 4x minus 1 equals 61. I can type log 561 into my calculator. Now, if I wanted it as an exact answer, I would say log 561 plus 1 over 4, obviously that x, what x equals. And you just leave it like that if it asks for an exact answer. This strategy doesn't always work. So it's not going to work when you've got something like this. So say you've got something like this. Because you've got them on both sides, the same strategy doesn't really work. So what we can do here is, as long as we use the same base, we can do what's called taking logs. So we can do logs of both sides. So I'm just going to use log, and in my calculator, I'd probably use ln, or I could just use log of the same the same base. So let's say this is log 3 to the x. So I'm going to do log of the whole of this side and log of the whole of this side. So whenever I have a log of something, as long as I do it to both sides, it's okay. The power comes in front. So we're going to get x log 3. And here we're going to get x plus 1 log 2. I can open out the brackets, x log 2 plus log 2. I can put all my x's on one side. X log 2 equals log 2. Take x outside the bracket. And I can make x a subject. And at this point, I would rearrange everything before I put it in a calculator. So when you put this in a calculator, you get 1.7095. And it won't matter what base you do it to, as long as they're all to the same base. So either use your ln button, which we said was to the base e. You could use your log button, which is to the base 10. Or you could use this button, but as long as you made this base the same number each time. And that's how you'd solve it if you've got something on both sides. So the last bit of this is actually looking more at ln and what ln actually means. So we said it's a log to the base e, which means e cancels it out. So kind of like a square and a square root cancel each other out. Putting something, logs and e's cancel each other out. So the inverse of e to the x would be ln x. So if we think of an exponential graph, so anything that's growing exponentially. So if we look at e to the x, we know that anything to the power of 0 is always 1. We know this is never going to go negative, because even if we had e to the minus 5, so think about e to the minus 5, or any number to the power of minus 5, and power just means 1 over. So we still get a fraction, we don't get a negative number. So any exponential graph always looks like that, and it'll have varying degrees of the slope. It should be going through the 1. So that's my e to the x graph. If I now take my ln x graph, it's going to do the inverse. It does this. So it never, ever, ever hits my y-axis, and my e to the x graph never hits my x-axis. So for this one, my asymptote is x equals 0. And for e to the x, my asymptote is here, which is y equals 0. So it's where you can never go below. But anyway, it doesn't really matter. It's just knowing that they're inverse of each other. So what I mean by that is if I do ln of e to the x, essentially these cancel each other out and it just leaves me with x. And if I do e to the power of ln x, they cancel each other out and leave me with x. So they're the opposite. So if I had e to the x equals 5, x is ln 5. So to get rid of the e, you have to ln it. So let's think about how we would then use that. So if you've got ln 3x plus 1 equals 2. To get rid of the ln, I e it. So I get 3x plus 1 equals e squared. So when you do e, it becomes a power. So x would be e squared, bring the 1 over, divide by 3. Right, what about if I had, let's take something a little trickier. Let's have e to the 2x plus 2e to the x minus 15 equals 0. Now the thing here, and this comes up a lot in A-level maths, is you get lots of what we call disguised quadratics. Because what this is the same as saying is e to the x squared plus 2e to the x, 15 equals 0. Now you've got two options here. You can go straight for factorizing, or you can say pick a letter, y equal e to the x. So you get y squared plus 2y minus 15 equals 0. If I could then factorize that in terms of y, I'm going to get 3 and 5. So I'm going to get plus 5 minus 3. So y equals minus 5, y equals 3, which tells me e to the x equals minus 5 or e to the x equals 3. Now to get rid of e, we do ln. We know we can't do ln of a negative number, so this one is not valid. And then here we get ln 3. So that's a disguised quadratics. That's one type which gives you a disguised quadratic. The other type of question where you end up with a quadratic is if you have something like this. So if you have e to the x minus 2e to the minus x equals 1, you could rewrite the e to the minus x as that, because when you have anything to the power of a negative. And what could you do? So we hate fractions. Fractions are annoying. We can't work with fractions. We're going to times everything by e to the x. So we have that squared. And we've got a disguised quadratic again. So you could let y equal e to the x. You've got y squared minus 2 equals y. Put everything on one side. Y and y, 2 and 1. You want minus 2 plus 1. So y equals minus 1, y equals 2. It tells you e to the x equals minus 1, e to the x equals 2. That one's not valid. This will happen in most cases with e to the x because they want to test that you're not trying to take ln or log of a negative number. So that takes you through, oh my God, my voice is going, most of the logs chapter. Now the rest of it is using that and taking a linear graph and making it into, taking a quadratic graph, making your exponential data, into a linear graph. Because what that does is it helps you plot things. What I mean by that is, for example, sometimes we have graphs that are not a straight line. So when we have a straight line graph, let's just start with that. When we have a straight line graph, it's really nice. We can get a plus c. So we get y equals mx plus c. We get a plus c, we get a gradient, and we can do lots with that information. We can think about the rate something is growing. We can think about what we're doing. Now, one of the things we use exponential graphs for, and that's probably for another lesson because it's a big part of the AS and it's what a lot of what's tested, is we use these exponential graphs. What we do is we convert them into linear graphs so we can do questions, so we can manipulate them, and so we can find out more information and answer questions. So if I just take it very theoretically to start with, if you had an exponential graph, it would be of the form y equals something to the power of x times by something. Now what I could do is take logs of both sides. So say I took log of this side and log of this side. Again, this is for another day, but this is just to give you a quick intro. Now what we can have here, this is the same as log a plus log bx. So the fact I haven't put a base means the base is the same. So log y equals log a plus, and the x can come in front here, x log b. Now if you notice, this now looks like y equals mx plus c, where my plus c is the same as this. My y is log y, so that's what I would plot on my vertical axes. I have x here, so my gradient would be the same as log b. And like I said, we can go through that on another day. So I hope that was useful. Leave any messages or questions that you have.